Hello everyone. Let us start fourth lecture, and today we will talk about phase diagram, and here we will concentrate on binary phase diagram. And in the last lecture, as we have mentioned, that there are two ways one can find out phase diagram. One is experimental route, and another one is thermodynamics route. And as we have mentioned that phase diagram is integrate part of heat treatment, because that initially that diagram gives you an idea that what sort of phases you would come across if you start doing treatment at a particular temperature and for certain duration of time. It gives you an idea that what would be the phases. So, that is what it is very important to know phase diagram of a system. So, first we will start with experimental route, and in phase 1 we talked about two phase diagrams. One was isomorphous, another one was eutectic, and today we will try to get isomorphous phase diagram as well as eutectic phase diagram, a simple eutectic phase diagram, from after doing a couple of experiments of series of alloy systems, series of alloy mixtures. Now, when we do experimental route, that time the first thing that comes into our mind, which is cooling curve. And let us talk little on cooling curve. Let us say we have taken a pure metal, let us say pure nickel, whose melting point is 1455 degrees Celsius. If we take nickel in a crucible and then take it inside a furnace, and also we connect a thermocouple in order to see the temperature of this nickel, and then we take the temperature of the furnace to around 1550 degrees Celsius, then all the nickel will melt. Now, after that we can keep it inside the furnace and put out the furnace, then we will see that the temperature is gradually going down, and the point when we are switching off the furnace, from that point onwards, if we try to see temperature variation with time, then we will get a plot like this. The temperature will gradually go down of this nickel piece, nickel melt. As per the furnace is cooled down, that particular situation, you will get a plot like this. The temperature of that melt is gradually decreasing, and as the temperature of the furnace is going down, because we have switched it off and it is cooling very slowly, so you will come across a kind of graph like this, where if we measure this particular temperature, we will see that this is around 1455 degrees Celsius, and there is a dip, and this dip in temperature we have also discussed before. This is called recalescence. This happens because in order to get some solid crystal in a liquid melt, we have to cross interfacial energy barrier. We have discussed it before, and that is what we have to have a sufficient undercooling. This we can call it as del T, which is undercooling, and during this undercooling we have corresponding del G variation, and that gives free energy, which is negative term, actually supplies the energy for the formation of interface. And once the first nuclei forms here the first nuclei forms, and then since the solid is forming, it has to eject the amount of latent heat which is required for solidification. Since it is leaving that much of heat to the melt temperature again goes up, and that is what we have a dip and then going up, and finally it reaches very close to the melting point. Rather it is little less than melting point, because at melting point nothing happens, and then it continues till all the liquid solidifies. And here we are not seeing that regular arrival of this recalescence, because that time already you have crystal solid nuclei. So, whatever heat you are taking out, and that heat is nothing but equivalent to the latent heat of solidification. And then once you have all the liquid turning up into solid, then again temperature starts decreasing along this path. So, this is basically start of solidification, and this is end of solidification, and this is start. But actually it is happening, if we see this particular plateau, this is happening at around 1455 degrees Celsius. So, this is a kind of cooling curve, we call it a cooling curve of pure metal, pure substance. Now, if we take an alloy, then situation differs. Let us say if I take 90% nickel and 10% copper, and if we take the temperature to 1550 degrees Celsius, then this will form an alloy, and since we know that alloy is nothing but a solution of two or more metals, here also it will form a liquid solution, which is nothing but alloy of 10% copper in nickel. Now, here since nickel content is more, so that is why we can say that it is a solid solution of nickel. It is an alloy of nickel rather, where we have 10% copper. Now, if this alloy we take, then we try to do the same experiment, we will get a cooling curve again. So, now as we understand that cooling curve is nothing but the temperature time plot as the metal is cooled down from liquid phase. Now, here initially it will cool down like this, where everything would be liquid. Here also if you see, till this range, it was all liquid, and once recalescence happens, then solid starts. Here also it will be all liquid, the liquid temperature goes down, but interestingly here the situation does not happen like this, rather it goes like this at a slope which is different than the initial slope. And then again after some time we see there is another, rather it would be, and this is 90% nickel plus 10% copper. And we can actually see that at this point solid appears, and at this point no liquid is left out, means all are solid. So, then we can say that this point we call it as liquidus and this point we call it as solidus. And here we have liquid, here we have complete solid, and this is nothing but an alloy of 90% nickel plus 10% copper in solid state. And in between, from liquidus to solidus, we have a mixture of solid plus liquid. We will come to this particular part later on, because these phases, we are just indicating phases, but the composition varies continuously from this point to this point. This point to this point, composition varies, and that variation of composition as well as the fraction of solid and liquid can also be determined once we get an idea of phase diagram. This is 90% nickel and 10% copper. Similarly, if we make it 90% copper plus 10% nickel, it would also form solid as well as liquid solid solution, rather solid alloy as well as liquid alloy, and that time we call it as an alloy of copper where 10% nickel is present. And in case of copper nickel system, we know that they can be mixed at any proportion in liquid as well as in solid state. So, if we try to follow this particular alloy and try to do the same experiment, that means putting it in the furnace, heating it at around close to 1400 degrees Celsius, sorry, here also you have to heat it till around 1550 degrees Celsius, melt everything. Once you melt everything, then they will form an alloy, and then you start cooling down, rather put up the furnace and then start seeing the temperature variation. There also we will see a similar plot, but if we see the same axis, this is temperature and this is time, if we follow the same axis, then we will see that the melting first solid that appears would be little lower temperature than these. I will come to that why it is that, and then here also this point also would go down little bit, and then finally you have a situation like this. This is also liquidus and this is solidus, and here it is liquid, here it is solid, and it is liquid plus solid. Since majority is copper and copper melting point is 1083 degrees Celsius, so that is what the entire temperature points for liquidus and solidus, they drop down. And finally, if we see 100% copper, again we will see the similar plot like what we have seen in case of 100% nickel. Again time, temperature, we see a plot like this, where the same thing happens what happened in case of nickel, only thing is this time the temperature would be, which is the melting point of copper, melting point 1083 degrees Celsius. And here also we could see a recalescence. In other cases also, in case of alloys also we do see recalescence, but the effect is lesser than, effect is not that significant in comparison to pure copper or pure nickel. Now here also in this zone I see that liquid is gradually converting into solid. So, it is a mixture of liquid plus solid, and here it is liquid and here it is solid, but in all those cases those are pure substance. And only difference is in case of alloy we have a slope, and we will come to know why that slope is, and here also we do not see any slope, it is a flat line which is horizontal with reference to time axis. Since the single temperature, all the solidification is taking place, but here we do not have a single temperature where solidification is taking place, rather in range of temperature where solidification is taking place, and the reason being there is a continuous change in composition. So now if we see this one, this is pure nickel and this is pure copper, and if we try to plot those solidus and liquidus points on a diagram where the axis is temperature and here the axis is percentage of copper. So, here 100% nickel and here 100% copper. Since in case of copper and nickel we are getting a single temperature where all the liquids are converting into solid. So, in case of copper we can point out it is 1083 degree Celsius and here it is 1455 degree Celsius, pure nickel melting point and pure copper melting point. Now, if we consider, as we have considered in case of this particular case where 90% nickel and 10% copper. Now, I just put a dotted line . This is 10% copper. We see that this point, if we try to compare with this point, this will be, this liquidus line is lower than the melting temperature. So, you just try to put that particular point, which is, I would say that this is L1, this is L1, this is S1. If I point at L1 as a liquidus and solidus is S1, and here it is L2 and this is S2, then this is my L1, and now the another temperature is S1. So, the same composition we are getting 2 points, liquid line, liquidus point and solidus point. Now, on the other side, if we try to compare, try to put these values here on the other side, this is, let us say, this is 10% nickel or 90% copper, then there would be 2 points again, and those points will be lying lower than these points. So, this would be here, this is L2 and here it is S2. Now, if I try to connect all the L1 point, L1 and L2, and if we can also get some composition midway, we can also get corresponding L, liquidus and solidus lines, points. Now, I connect those, and gradually if we take it down to pure condition and then I join the liquidus as well as solidus points, I get a plot like this, where the final plot becomes this. And so, above L1 everything is in liquid, and below S line everything is solid. In between, as we have seen that there is a mixture of solid and liquid, here also is a mixture of solid and liquid. So, we say that solid plus liquid. Now, what we are getting is a phase diagram which we call it as isomorphous. Phase diagram. And now, let us look little more into the isomorphous phase diagram, because that is also crucial. Now, if we try to draw an isomorphous phase diagram, what we have seen in case of nickel copper, this is 100% nickel, 100% copper, and percentage at copper increases this way. This is temperature. Now, let us take any compositions like this, and if we take any composition, let us say we have taken 40% copper. If we take the temperature to this level, everything would be liquid. That means we can say it is a liquid alloy, and if we can take it to this, we can say that it is a solid alloy. But when it cool along this line, first time when it touches this point, which is basically liquidus line, where first solid appears, the first solid would appear here. Now, if we have a melt like this, where some solid crystals are forming, then there will be compositional changes. So, now once you have it, the first crystal forms, first solid, and that solid will have composition here, and the liquid composition would remain here, because it is a tiny change. So, overall composition would not change, or the liquid composition would not change much, but the first tiny crystals would be having composition at this point. Now, still we cool it down further, then if we cool it down further, so if I reach to this temperature, we will see that there would be liquid phase and there will be solid phase, and the liquid would have composition here and solid would have composition here. This is solid, this is liquid. Here it is basically nothing but the composition, X copper solid, and this we can say that X copper liquid. And interestingly, we can also calculate what is the mass fraction of both the phases, liquid and solid. We can say that if we connect it as A, B and C, we can say that AB by AC, this is the fraction which is the content of liquid with a composition X copper liquid, and BC by AC equal to content of solid with a composition X copper solid, and this is coming from lever rule, which simply follows mass conservation. Now, as we see that the composition is changing as we are going down, mainly the liquid composition is changing. See, the liquid composition is here. Now, when we cool it, we are getting a plot like this. Now, interestingly, at this point, which indicate this point, first solid appears. As we are going down, then we are changing the composition of the liquid as well as solid. The solid which would appear is basically varying along this line. That means, as well as the liquid which would get solidified is also varying along this line. So, every time I am seeing there is a lowering of solidification temperature. So, that is what it takes a shape like this. Though we have drawn it like this, it may not be same as what it is a flat line, there could be a curve like this, because every time the amount of latent heat that is also changing, at the same time heat extraction rate would also change depending on the condition of temperature at the surface. So, that is what you have a slope like this and typical shape of cooling curve. So, now later on we will also check what would be the microstructure which is also important, how the microstructure evolves as we go down in that along this particular any composition line in case of isomorphous system. That is also very important aspect, because finally during heat treatment we are aiming at some particular microstructure. So, how the microstructure evolves, that is also an important aspect, and we will also consider this part later, little later, but we have now seen that how experimentally one can determine a phase diagram. We have given example of isomorphous system in case of copper and nickel, and now in the next lecture we will try to see how an eutectic phase diagram be drawn from simple cooling rates, and that cooling rates can be found out, not cooling rate is rather cooling curve, and those cooling curves can be found out from a simple experiment. So, let us stop here. Now, in the next lecture we will try to get into eutectic phase diagram and how to get eutectic phase diagram from cooling curve determination. Let us stop here. Thank you.